So, good morning and welcome to my stream. And the sound seems alright. Okay, then, yeah, let's start with day 12 of Advent of Code, and sadly the last day for this year. Yeah, normally there are 24 days or 24 tasks, but this year they reduced it to 12. But yeah, let's make the best out of it. So, day 12, Christmas tree farm. You're almost out of time, but there can't be much left to decorate. Although there are no stairs, elevators, escalators, tunnels, chutes, teleporters, fire poles, or conduits here that would take you deeper into the North Pole base, there is a ventilation duct. You jump in. After bumping around for a few minutes, you emerge into a large, well-lit cavern full of Christmas trees. There are a few elves here frantically decorating before the deadline. They think they'll be able to finish most of the work, but the one thing they are worried about is the presents. For all the young elves that live here at the North Pole, it's an ancient tradition to put these presents under the trees, but the elves are worried they won't fit. The presents come in a few standard but very weird shapes. The shapes and the regions into which they need to fit are all measured in the standard units. To be aesthetically pleasing, the presents need to be placed into the regions in a way that follows a standardized two-dimensional unit grid. You also can't stack presents. As always, the elves have a summary of the situation, your puzzle input, for you. First, it contains a list of the present's shapes. Second, it contains the size of the region under each tree and a list of the number of presents of each shape that need to fit into that region. For example, and here those are the shapes and their index before it. And here we have the spaces we have under the tree. So the first section lists the standard present shapes. For convenience, each shape starts with its index and a colon. Then the shape is displayed visually, where hashtag is part of the shape and dot is not. The second section lists the regions under the trees. Each line starts with the width and length of the region. Here 12 by 5 means the region is 12 units wide and 5 units long. The rest of the line describes the presents that need to fit into that region by listing the quantity of each shape of present. So 101032 means you need to fit on one present with shape index 0, no presents with shape index 1, one present with shape index 2, no presents with shape index 3, 3 presents with shape index 4, and 2 presents with shape index 5. Presents can be rotated and flipped as necessary to make them fit in the available space, but they have to always be placed perfectly on the grid. Shapes can't overlap. That is, the hashtag part from the different presents can't go into the same place on the grid, but they can fit together. That is, the dot part in a present shape diagram does not block another present from occupying the space on the grid. The elves need to know how many of the regions can fit the presents listed. In the above example, there are 6 unique present shapes and 3 regions that need to be checked. The first region is 4 by 4. In it, you need to determine whether you could fit 2 presents that have shape index 4. After some experimentation, it turns out that you can fit both presents in this region. Here's one way to do it, using A to present one present and B to present the other. Yeah, this is shape index 4, and if we flip it, they can fit together into one another. The second region, 12 by 5101022, is 12 units wide and 5 units long. In that region, you need to try to fit one present with shape index 0, one present with shape index 2, 2 presents with shape index 4, and 2 presents with shape index 5. It turns out that these presents can all fit in this region. Here's one way to do it, again using different capital letters to represent all the required presents. Okay. I'm currently looking at the shapes here, how they're fitting together. The third region, is the same size as the previous region. The only difference is that this region needs to fit one additional present with shape index 4. Unfortunately, no matter how hard you try, there is no way to fit all of the presents into this region. So in this example, 2 regions can fit all of the listed presents. Consider the regions beneath each tree and the presents the elves would like to fit into each of them. How many of the regions can fit all of the presents listed? So, yeah, that's actually a problem I have never encountered before. So I'm actually not sure how one can go about this. So what, how can you, how do you even start doing this? Like, where do you try to put the shapes? How do you try to insert the shapes? Is there any algorithm that... Okay, let's look at the shape index 4. So this is 101032. So shape index 4 was this one. So this needs 3 by 3 space, essentially. Yeah, that probably wouldn't fit anywhere. But how do you determine that it won't fit? I cannot imagine an algorithm for that right now. That actually sounds like quite the interesting paper. But it's probably behind a paywall, right? Yes, of course. And I wouldn't read that paper here. um, let's see what... The packing problem, okay. Without knowing what kind of shapes you are likely to face ahead of time, it can be very difficult, if not impossible, to come up with an algorithm that will give you the best answer. More than likely, unless your polygons are nice polygons. Sorry. Circle shapes, equilateral triangles, etc. We'll probably have to settle for a heuristic that gives you the approximate best solution most of the time. One general heuristic, though far from optimal, depending on the shape of the input polygon, would be to simplify the problem by drawing a rectangle around the polygon so that the rectangle would be just big enough to cover the polygon. Once we have done this, we can take the rectangle and try to fit it as many of that rectangle into the large rectangle as possible. This simplifies the problem into a rectangle packing problem, which is easier to solve and wrap your head around. Here's an algorithm for that. Yeah, now obviously this heuristic is not optimal when the polygon in question is not close to being in the same shape as the rectangle, but it does give you a minimum baseline to work with, especially if you don't have much knowledge of what your polygon will look like, or there is high variance in what the polygon will look like. Using this algorithm, it would fill up large rectangles like so. The same image. For the case of the T-shaped polygons, the heuristic is not the best it could be. In fact, it may be almost the worst case scenario for this proposed approximation. But it would work very well for other types of polygons. Okay. Let's look at our puzzle input. Okay, there are only very few shapes, but there's a huge number of things we have to get under it. So there must be some form of efficient packing algorithm I am unaware of. Packing algorithms. So packing problems are a class of optimization problems in mathematics that involve attempting to pack objects together into containers. The goal is to either pack a single container as densely as possible or pack all objects using a few containers as possible. Many of these problems can be related to real-life packing, storage, and transportation issues. Each packing problem has a dual covering problem, which asks how many of the same objects are required to completely cover every region of the container where objects are allowed to overlap. In a bin packing problem, people are given a container, usually a 2 or 3-dimensional convex region, possibly of infinite size. Multiple containers may be given depending on the problem. A set of objects, some or all of which must be packed into one or more containers. The set may contain different objects with their sizes specified for a single object of a fixed dimension that can be used repeatedly. Packing in infinite space is not what we need. Hexagonal packing of circles is neither. Okay. Packing in 2-dimensional containers. Packing of squares. People are given n unit squares and have to pack them into the smallest possible container where the container type varies. I mean, they are not squares. Packing identical rectangles in a rectangle. The problem is NP complete. Nice. I must be overlooking something. I mean, they wouldn't they wouldn't ask for you to win the Turing Award to solve this task. And solve an NP-hard problem in n time. I mean, what they did here, I mean, we only have 5 shapes. We could actually manually look at these shapes and manually find ways of stacking them together well. I mean, here they use this pattern, this stacking d4 into d4 and then flipping it around. That could be used as a rectangle, right? We could spin up a rectangle that goes directly around these. Then for A and F, we could do the same, but here they stacked them into one another. So that won't work. But we cannot brute force this. I mean, if we look at this, if we try to brute force this, we end up with the same problem I had yesterday. And we have way too many solutions. That won't work. That definitely won't work. That sounds good. In tiling or tessellation problems, there are to be no gaps, no overlaps. Many of the puzzles of this type involve packing rectangles or polyominoes into a larger rectangle or other square-like shape. There are significant theorems on tiling rectangles and cuboids and in rectangle with no gaps or overlaps. An A times B rectangle can be packed with 1 times n strips if and only if n divides A or n divides B. A box can be packed into a harmonic brick. The box has dimensions. Study of polyomino tiling largely concerns 2 classes of problems: to lie a rectangle with congruent tiles and to pack one each n-omion. A classic puzzle of the second kind is arrange a 12 into rectangles of size. Okay. Packing of irregular objects is a problem not lending itself well to closed form solutions. However, the applicability to practical environmental science is quite important. For example, irregularity-shaped soil particles packed differently as the size and shapes vary, leading to important outcomes for plant species to adapt root formations and allow water movement in the soil. The problem of deciding whether a given set of polygons can fit in a given square container has been shown to be complete for the existential theory of the reals. Yeah, Tetris is... The bin stacking packing problem sounds actually like what we are currently facing. The bin packing problem is an optimization problem in which items of different sizes must be packed into a finite number of bins or containers, each of a fixed given capacity, in a way that minimizes the number of bins used. Yeah, that's... Yeah, I already... I thought about that as well. Like, similar to how they are doing it here. Here they are stacking the 4 shape together. So yeah, this one here. And maybe it does make sense to first look at the shapes and find orderings for them manually, and then try to fit those orderings into the space. But of course, that doesn't guarantee that the solution we come up with is optimal, right? I mean, maybe it would be better to not fit them together. Yeah, but maybe that is the best solution. And then looking at these tiles as rectangles, blocking entire spaces out could be a solution. But still, it feels like we would have to brute force parts of it, or try different rotations and different packings, and still doesn't feel right. But it's just, yeah, probably just me not wanting to implement it and not really a problem with the task. Okay. Okay, so bin packing problem in which items of different sizes must be packed. Minimize the number of bins used. That is not really the problem here, but we could theoretically try to... I mean, theoretically, we could try to split the areas here into bins. Yeah, but I think the idea of trying to put them together directly is still the best idea. Like pre-processing them manually is probably the best thing. Let's look at Tetris. Or is this just the game Tetris? Yeah, that's just the game Tetris. Okay. I thought there was a Tetris problem. So, covering problems. In combinatorics and computer science, covering problems are computational problems, the tasks that ask whether a certain combinatorial structure covers another, or how large the structure has to be to do that. Covering problems are minimization problems, and usually integer linear problems whose dual problems are called packing problems. Okay. The most prominent example of covering problems are the set cover problems, which is equivalent to the hitting set problem, and its spatial cases, the vertex cover problem and the edge cover problem. So, in the context of linear programming, one can think of any minimization linear program as a covering problem if the coefficient in the constraint matrix, the objective function, and right-hand side are non-negative. More precisely, consider the following general integer linear program. It's been some time since I've been using linear programming. Wasn't my best subject. At least I'm not using ChatGPT, okay? But I'm very close to doing that. For everybody not not speaking German, yeah, exactly. For everybody not speaking German, he asks if he is disappointed. Yeah, I mean, ChatGPT could be a help in finding a viable algorithm. So, like doing the research here. But otherwise, you're of course right. I don't think that ChatGPT could come up with a solution. But what I've seen on Reddit was not regarding this problem, but another one was that somebody directly had an suggestion by Copilot by simply pasting in the description, and Copilot directly had a pre-formulated result. It was with a screenshot. I trust screenshots. So, but I don't think using the covering problem here will result in anything useful. Ah. So the task is you are given these shapes and you are given areas and the task to fit certain shapes into those areas. So here the index of these numbers here relate to the different shapes. So this is how often you have to fit this shape, and this is how often you have to fit this shape. And you need to find out if you can stack these shapes into the areas that are provided. And yeah, so here like this, for the first example, we have 4x4 and we need to fit shape 4 twice. Yeah. Like, for example, you have this shape, you need to fit it twice into a 4x4 grid. This is the 4x4 grid. And you can stack the shape 4 into itself like this. And then you can fit these shapes into that box. Yeah, exactly. And you have to find this for here. In this example, you have to do it for a 12x5 grid and fit the shapes into it. Here, the different letters mean that those are different shapes. So this is the one shape, the D, and this is the other shape. And yeah, you have to fit them all into this grid. And I mean, this looks all right, but the actual input we have is more like this. And I'm pretty sure that brute forcing here won't work. Right now, I'm neither. So, like these, I'm not even sure if you can call these geometrical. I mean, it's a covering problem, or a packing problem. And there are solutions for packing problems, but they are not optimal. Not yet. Writing a brute forcing algorithm in Rust would still take me some time to even come up with an idea how to brute force that better than just laying one shape at every position and then laying the next at positions that fit, which is just so terribly inefficient that I won't even try that. Because, I mean, if we only look at the first one, 42 shapes. So, yeah, you have way too many possibilities how you can lay them into that grid. That doesn't make any sense. So one idea we had here in the chat was to like one idea in the chat was to stack them together, or yeah, like first looking how how are the shapes related to one another, and then trying to fit them into each other and look for the shapes. If we can cover good ground here. I mean, that would make sense for some shapes, definitely. I mean, for this, for example. And for this, we can, by stacking them together, fit them into 4x4 grids. For this, the same way. And only you lose one space each. And yeah, then we could look at them like they are rectangles and simply plaster them across the space. I see the ideas are getting more and more sophisticated. That would probably, yeah. Maybe OpenAI can do that. Ah, okay, nice. But I cannot. So there was this, but the Columbia University took that article down, apparently. But let's look for the packing problem and maybe find a solution. That's not what we need. Yeah, we already were here. Each pairing has a dual decovering problem. So the dual problem, if you can solve the dual problem is the counterpart to the actual problem, like generally speaking, that's the definition I still have in my head. And if you can solve the dual problem, that proves that the actual problem can be solved. It's part of linear programming, but I don't want to use linear programming here. So there is the rectangle. I don't think using a different search engine would result in better results. So, packing identical rectangles. Rectangle packing is a packing problem where the objective is to determine whether a given set of small rectangles can be placed inside a given large polygon such that no two small rectangles overlap. That's exactly what we want here. Packing identical rectangles, packing identical squares, packing different rectangles in a given rectangle. In this variant, small rectangles can have varying length and widths, and they should be packed in a given large rectangle. The decision problem of whether such a packing exists is NP-hard. Nice. This can be proven by a reduction from 3 partition given an instance of 3 partition. Yeah, okay, if this problem is, if the decision problem alone, so if there is even such an alignment, then I don't think we need to solve an NP-hard problem. Packing different rectangles in a minimum area rectangle. In this variant, the small rectangles can have varying length, right? Varying lengths and widths, and their orientation is fixed. The goal is to pack them in an enclosing rectangle of minimum area with no boundaries on the enclosing rectangle width or height. This problem has an important application in combining. The problem is NP-complete in general, but there are fast algorithms for solving this. Maybe. It's far too early for me to read some informatic kram in English. I only read informatic kram in English. So maybe the idea that was proposed earlier is actually the solution here. Let's quickly switch over. Yeah. I don't know, it's easier to, I think that it's easier to reach people in the informatic area if you simply use English. Everybody speaks it. So, but my idea would be, okay, so let's, yeah, use that shape. I think it's, so we could stack that space. I think I'm misaligning it, yeah, like this. So this would now be a 3 by, no, a 4 by 4 shape. I think if we can make all of these shapes 4 by 4 by stacking them together, like the one person proposed, if we stack them all together like the one person proposed, we can actually get a 4 by 4 shape for every shape, and then the problem isn't NP hard anymore because it's the one problem on Wikipedia. Switching over again. Packing identical rectangles in a rectangle. In this, we are multiple instances of single rectangles of size L times V, W, and a bigger rectangle of L times W. The goal is to pack as many small rectangles as possible into the big rectangle without overlap between any rectangles. Common constraints of the problem include limiting small rectangle rotation to 90 degree multiples and requiring each small rectangle is orthogonal to the large rectangle. This problem has some constraints as box specifying wood pulp stowage as an example result. It's, yeah. Yes, I think, I definitely think that that could be a solution here. But I really have a problem with rotating this right now. Okay, so here we have 2. So remove this, make a dot. Here we have 2. And then we have 3. Yeah. Yeah, so this should be the shape mirrored. This is now also for... Okay, this is 4 by 5 now. Yeah, and this shape can't be really meshed together with the other one either. But we know that we can make a 4 by 4 shape out of this. This is now 4 by 4. And we've seen that they did it like so. Which is not 4 by 4 either. This is 5 by 4 again. So 2 here, 3 here. I actually don't understand that question. But isn't there the problem if you pre-build a würfel, so a dice, that you can't get all the numbers? Did you have a stroke? Ah. Yeah, okay, okay. So, uh, the explanation here, when you build a dice, you build it out of 3 parts, and you can only you can only um reach results that are divisible by 3. Yeah, I think one of the Wikipedia pages also had a similar problem that you can only that you can only have that the decision problem will boil down to divisibility. Actually, I think I'm gonna cheat. I'm gonna look at Reddit, at the subreddit, and I'm gonna see what they are currently up to. Is there a link here? No. Okay. Hmm. Yeah, no, we don't want Alexandria Ocasio-Cortez. I always... Okay, so let's look for day 12. Yeah, okay. Solution, try to determine if they want to fool you. It would be smart, regardless, to lower the amount of challenges given, so I was not even trying to see if they'd fool me, but okay, good. Okay, they are certain that this is an NP hard problem. Was I just lucky, or is it by design? So let's see where I... So first thing I tried today was just count how many grids can actually fit presence by area without even taking shapes into account. Easy, yeah, okay, count the hashtags in the present shape and multiply by desired count and see its sum is less than area to fit them in. Yeah. Okay. If that is the solution, that is, of course. Okay, that would be way too easy. Yeah, not way too easy. You have to come up with it either way, but the problem seems way harder. But let's try it. Maybe that person was just lucky with their input, but I don't think so. Most of the time they are The problem is there's some easy solution if you look at the actual input. So I'm simply copying what I had from a previous day. This is currently grayed out because I haven't added it to the crate. I'm gonna copy over the test input real quick so that we have our test case here. So, and the result was 2. Let's assert that, and then let's head over to our module and do it like this. And then here we want to import day 12. Okay, and then now our task would simply be to find the different shapes and then simply count if they even are, if they can even be passed into here. So let's simply see. Even for reading in, we need a state machine. What is wrong with the task today? So we split our input on \n, and I would use a for loop for this right now. And a line. So then if the first is a number, if the first isn't a dot or 0, a dot or a point, we know we are no longer so we are splitting on \n. I may need a regex here. I mean, we know we have these 5 shapes. We could just make it simple and simply skip over these. It feels dirty, like cheating, but I don't know. I don't want to overcomplicate things here. So we simply come to the dark side. So this is the shapes. It's an answer type. And then we can simply say skip shapester split on \n count. Yeah. But I mean, for this problem, I think it's completely fine to simply hard code it. I mean, there are only 5 shapes. We can simply put them in. So let's use these shapes. Let's make a struct for that. Maybe let's put that down into the region of shame. by doing that, we can hide it later by simply collapsing it. Okay, so then let's define a struct, which would be a shape, and a shape has an index, which is a usize. And we don't actually need the shape, but let's do it anyway. Yeah, let's name it content, which is an answer. And then it means element count, which is of type num for us. And if we want an answer, we of course need a lifetime, but we could also say that this is simply static. That means that it must be constructed before, before our, must be constructed before our program runs. So then we can make an impulse for the shape and say from stir input answer, and or we just name it content because this will be our content, and it returns a self, so the shape, and then we make a self, put in the content. You also have to put in the index, which is the usize. Index, not usize. And then we can simply say content. No, actually, I did not miss a semicolon. In Rust, if you don't write a semicolon at the end of the last statement, this means that it is the return statement. So I could write return this, or I can simply do it like this, and this is essentially the same. We probably just wanted to make a stupid joke, but there's actually merit to what you said. So let's say chars filter where C is equal to the hashtag symbol, and then count that, and that is our element count. And then you can say element count. And we have to dereference here. I said that this would be a num and not. So what's your problem with content? The lifetime may not live long enough. Of course, we have to define that this must be static. And I think we cannot make this const. No, we cannot, of course, because of the iterator here. Yeah, then we have to use... we can define it in the function. We can simply say construct shapes. Yeah, I mean, C and Java, I mean, they all have a similar syntax, but yeah, it's I get it definitely. They all essentially look the same. The good thing is most of the time they do the same. Yeah, like JavaScript, yeah, definitely. I mean, I could do this in JavaScript, but I could also shoot myself in the head. That would also work. No, but Python or JavaScript could be used here, but JavaScript, I mean, I don't know. If I would use a different language than Rust, I would either use C# because I use it all the time, or I would use Python. What's TOS? Yeah, I thought so as well. I have to be more have to be more critical to what I say in this context. Still not used to streaming. Yeah. How would you translate that to English? Is there even a concept of a yeah, you can't. You literally can't. Anzeigen Hauptmeister. Definitely. Okay, so let's use a vec of shape here. That's what we will return. And then let's repeat that shape from stir. We actually need that 4 more times. And then we need the one shape. No, so it's one. I think there are 5 shapes. Yeah, okay. So then this one. And this one. And this one. Okay, so we have our shapes and can we, yeah, it's formatted. Okay. So then let's say let shapes is equal to construct shapes. And then we have the shape count and then, okay, so now these lines should be the lines down here. So we have our grid, XX. Yeah, I need regex here. Or I could split on colon chief reporting officer. It doesn't have the same ring to it. Just doesn't. Okay, I could split on the colon and then split that on the X. So line split on colon and then let select that. I think that's that is also that joke is under the niveau I want to keep up in this channel. So, and this we split on X. And then we need to collect that as well. And this probably doesn't know what to collect into, so let's define that we need a vec here. Exactly, and the same goes for this. Okay, and then we split on X, yeah, and then we get let grid dims, and then we can say X, Y is equal to grid dims. Do we even need the grid dims? No, we don't actually. We just need to know grid size. We can actually simply say we're split it. We map the dims we have here. We map them to we pass them. That's what I was looking for. I would simply parse as I64s, then we unwrap because we know they will definitely fit, and then we reduce by simply multiplying them with one another. Yeah, so that would be our grid, and then we unwrap. So this is the grid size, and then we have the right side of this part here. There we first, yeah, we need the right side of the part, so that would be, so part at position 1 is now something like this. And that means we first trim it to not have the prefix of just a white space. And then we split that on space, and then we map that again by parsing. Yeah, parse. We also use I6R. This could be usize. Let's also make it num and unwrap. But I actually want to enumerate this so that we also have the index. And then we can say collect into a vec again. And then this is our shape count. Thanks for the follow. I'm getting used to the sounds. In the beginning, I was always so confused when that happened. The first time someone rated this channel, I was in deep shock for a few seconds. Always forget that I added those. Okay. So. No way. You guys don't even hear the sound? I'm the only one who hears it? Yeah. Okay. There was no sound? Or are you trolling me? Yeah, okay. No, you would definitely not have overheard it, so I fucked up the settings. Thanks for telling me that. Then I know that I have to look at that and fix that again. Okay, so where was I? We have the shape count, and then we simply need to go over the index and the count in the shape count. Yeah, we didn't even need to collect it here, but that's all right. And then we look into our shapes at position ID X. And from there, we take the element counts and multiply it by the count. And we can actually use a... Yeah, okay. Yeah, I definitely... Okay, I definitely have to look into that then. Thanks, you guys. Okay, so we do a fold here. We start with 0, and then we take the index and the count. So fold is like reduce, but with the start element. And so then we also need the accumulator here, and then it's accumulator. So what we already have, like the 0, added with shapes at the index position. There will be a dereference here. And that multiplied by the count. And I have missed something apparently because... Okay, so the compiler isn't happy with me, but I'm unsure as to why right now. Oh. I deleted one bracket too many. We can simply say that you are an I64. And then I think we have to dereference the count here. No, what's the problem now? Okay, yeah, of course. Valid lines, which is equal to 0. I was returning the wrong result here. We cannot simply sum this and return that. That doesn't make any sense. But what we have to do here, I think this dereference is wrong. This is shape elements count. Let's call it like that. Here we have to use, yeah, and then we can say if shape elements count is smaller or equal to our shape count, wait, no, to our grid size, then we can increase the valid lines by 1, and in the end we can return the valid lines. So let's see our test. Failed because we had a parsing error. Okay, so where did we have that parsing error? In the reduce. Okay. What's the error? Unwrap on an error value. Okay. Interesting. Then let's have a look here. Apparently we cannot parse there. Probably because somehow the input is still messed up. Yeah, missing a semicolon. No, it is not a semicolon that is missing. That is definitely not the point here. So we have our part at 0, and that is 4 by 4. Split, that should be all right. Yeah, okay, that is no problem. Then we have 12 by 5. That is also no problem. Again 12 by 5. Again no problem. Yeah, okay, and then there is an empty string, and that is simply because I added a line here. That was my fault, I guess. Okay, so now we get 3 valid lines, but we need 2. That is unfortunate. I mean, we can look at the test input again. Yeah, yeah, okay, no. So in the test, this definitely does not work. But we can, of course, simply take this puzzle input and pray to the binary gods that using this for the actual input will work. And then we go to our main and we simply run this. Actually, I'm afraid of day 11. If I did not exclude the B part, then that could actually lead to a crash, because yesterday my stream crashed like 3 times. And that's actually okay. That's actually really mean. Like they may make such a hard test problem just to make the solution that easy. That's really mean. So that was day 12, part 1, the last day of Advent of Code. And yeah, well, I would have loved to do part 2. I need to get all the stars to even start the task. And yeah, I will try to get all the stars in the next streams and try to finish all the tasks there. And yeah, maybe do a little bit more cheating like I did in this stream. And yeah, the next stream will be on Tuesday the 16th and then on Thursday the 18th, always at 8 p.m. Yeah, maybe I will see you there. Afterwards, there will be Christmas and everything, so I won't be streaming for some time, but I will keep you posted when I'm back online and yeah, back streaming on a regular basis. So thank you very much for watching and see you in the next one.